Hello and welcome to another video. In this video we're going to be discussing prime factorization, and this isn't talked about too often in LeetCode, but you are going to need it in problems, so you're going to want a good way to do it. So we'll talk about the definition, kind of intuitively how you would do it, and then actually how you would have a pretty good optimized way to do it. So first of all, the definition, it's all the prime factors of a number including duplicates. What do I mean by that? So let's say we have a number like 15. It would basically be all of the factors, so it'd be like 3 and 5. And what I mean by including duplicates is, let's say instead of 15, we had 15 times 3, so let's say we had 45 here. So this would be 3, 3, and 5. And so the prime factors would be all of these numbers. So first of all, let's start with like an intuitive way to get the prime factorization of a number. So that's pretty straightforward. Let's say we just take a random number like 150. The way to do it is we can just keep breaking it down into halves, and then we can figure out for each part, can we simplify this further? So we can do something like, let's just say like 75 and 2. And then can we break down the 75? Yeah, this could be like 25 and 3. And for 25, it's like 5 and 5. So can we break anything else down further? No, we can't. So our prime factorization here is going to be 2, 3, 5, and 5, right? Because then we get 25 times 6, which would be 150. So that's pretty much how you do it intuitively. You just keep breaking it down into factors and then see if you can keep breaking your factors down more, right? It's like basic math. But the question is, how do you do this in code? So we're going to talk about kind of like a brute force way, and then we'll talk about an optimized way. So the brute force way is, let's say we take some number. Let's just say 150. What we can do is we can loop from 2 to n and just check if the number we're on is a factor. If it is, divide and store as much as we can. So what's that going to look like? Well, let's take a look. So we'll have like a result array. So we'll have result here, and then we'll have an n. So n will be 150. And we're going to start looping from 2. So we'll say like, okay, is 2 a factor 150? The way to check if it's a factor, we can just mod, right? So if 150 mod 2 equals 0, it is. So this is a factor. So in that case, this is a factor. So essentially what we'll do is we'll just say, okay, if it's a factor, we'll write it in, and we'll take our 150 and just divide by 2. So we get 75. Then we try again. Is 2 a factor of 75? No, it's not. So we'll go to the next number, 3. Is 3 a factor of 75? Yes, it is. So we're going to write in 3. We're going to divide 75 by 3. Now we'll get 25. Then we'll try again, because you can have a bunch of 3s, right? So for this one, 3 is no longer a factor. So we'll keep going. And then 4 is also a factor. Or sorry, 4 is not a factor, so we'll skip that. Then 5 is a factor. So we will divide by 5, write in the 5 as a factor. Now our number is 5. Then we try again. Is 5 a factor of 5? Yes, it is. So we'll write another 5. And now our number is 1. And you can have all kinds of ending conditions. One being if factor, I guess the best one is if factor is greater than our n, then we can just break, right? Because let's say our n is actually, in this case, you wouldn't want this condition. You would just want if n equals 1. So you keep looping until n equals 1, right? So if n equals 1, then we can break because we have all of our factors. And let's think about the time complexity for this algorithm, right? So essentially we are looping through every single number 1 to n, and then we keep trying to divide it by that number. So looping 1 to n is going to be O of n. And now also, let's say we have a number like some big number, like 128 or something. If we keep trying to divide it by 2, and we divide it by 2 a bunch of times, every division is going to be, like, if you combine all of the times we can divide a number by 2, all of those combined will be log n, right? So this will be log base 2 of n. If you try to divide by 3, it'll be log base 3 of n. Try to divide by 4, it'll be log base 4 of n, and so on. So our total loop through the numbers, 1 to n, will be O of n, and then for each number, we can divide it log n times. So this solution is going to be big O of n log n. And just the bases of the log will change from log 2 to log 3 and so on. Worst case, it'll be log 2, so this will be our solution. So we can actually do something more efficient here. And notice how we looped from 1 to n. We can actually do better. So we're going to show a better way to do it. So let's take, let's see, let's just take another number. Let's just take some number like 956. So we'll write that down. So this is going to be a two-step process. Step number 1, divide by 2 as much as we can. And store all 2's. So the reason this is going to be helpful is because if we divide by 2 as much as we can, our n at the end will be odd. So then we don't have to go 1 to n, first of all. Like we can go through only odd numbers. So that helps us a lot, right? Then there's going to be another simplification that I'll show after we do this part. So we have 956. Let's just see what happens if we just divide by 2 a bunch. So this divided by 2 once would be 450, 475, 478. So this will be 478. And we have a 2. And obviously we could divide this by 2 again, so we get 239. Now we can't divide this by 2 anymore, so now we're guaranteed to have an odd number, and all of the rest of the factors will be odd from now on. So we have to choose. Okay, now for this 239, we basically need to figure out how far we need to loop. So if you think about it, if you think of a factor, if you think of a number, right, n, and it has 2 factors, one and the other one, you're guaranteed, if the factors are not just like 1 and n, you're guaranteed for one of the factors to be less than root n. Because if you have some factor 1 times factor 2, if one factor is greater than root n, right, like let's say, for example, our number is like, I don't know, what's a good number? Like 81 or something. Root will be 9. So if one factor is greater than 9, let's just magically say like 15 was a factor, then the second factor would have to be less than root 9, right? And that's kind of the idea, is if one factor is less, if one factor is greater, then the other one is less. So then we can always just keep finding the smaller number, and then we can keep reducing our number, right? And that's kind of the idea. And then if 15 had more factors, then we would reduce that, and so on and so on. So you can basically, instead of going from 1 to n, you can go to root n, because one of the factors is guaranteed to be smaller than root n, or they're just both root n, like 9 and 9. But you're never going to have like 15 and 16 or something, right? And that's kind of the idea. And also, if 15 wasn't prime, then you'd be able to break that 15 down into more. And if 15 is prime, I'll kind of show what to do there. So that's the second part of the algorithm, is loop. We're going to start at 3 to root n. And this is going to be, to root n. And if root n is like 4.5 or something, you can just loop to this. Like, this is going to be basically the same. So we'll loop to this, and we'll check only odd values. Checking only odd values. So in time complexity, this doesn't actually save us anything, because if we check odd instead of all, it's still O of n. But now we got it down to square root of n, which is significant, right? So if we have like 400, now it's 20. That actually does make a difference. So that's the next part. So let's do that. For this 239, this is going to be kind of annoying, maybe. Yeah, I don't even, like, this honestly might be prime to begin with, but let's just see what happens. So for 3, it's not divisible by 3. For 5, it's not divisible by 5. For 7, it's not divisible by 7. For 9, I don't think so. Yeah, it's not divisible by 9. It's not divisible by 11. So let's just say, maybe this is like not the best example, but let's just say that there might be a factor here. I'm not exactly sure. We can test it out later. But let's say this was completely prime, right? So we would loop from like 1 to square root of this. Let's just say the square root of this was like, just make up some random number, like 15 or something. So if the square root was 15, we would loop from 3 to 15. We wouldn't find anything, right? We wouldn't find any factors. Then what would happen is n would still be 239. Then for the last part of the algorithm, we can say if n is greater than 1, add n to the factors. right? And so our factors here would just be 2, 2, and 239. And we can still have that early break. So if at any point, we can write this down as well. So if at any point n is less than the factor, we can just break, right? Because there's no way like if n is less than a factor, it's gonna be, we're gonna find anything in this loop, right? So like let's say n was 3 and our factor is like 7. Well, obviously 7's not going to divide into 3, 9 won't divide into 3, 11 won't divide, and so on. So this is the 3 parts. So this part is, well, we can write down the time complexity for all these. Part 1 is log n. Part 2 is root n, right? So square root of n log n. And the last part is O of 1. So now we got our time complexity down to this. And let's go through one other number maybe that's better than this to demonstrate this again. So let's say we'll hopefully do like, let's just do something that we know has a bunch of factors like 160. So first we're going to divide by 2 as much as we can, and we're going to take all the 2's. So let's see how many times we can divide by 2. So we can have 2 and 80, 2 and 40, 2 and 20, 2 and 10, and 2 and 5. And now notice that once we divide it by 2, now the numbers we have to loop through, instead of looping from 1 to 160, this in practice actually makes it a lot faster, because not only do we not loop from 1 to the original n, we're looping from 1 to this reduced n. So if it divides by 2 a lot, this will be really small. Actually, we're looping from 1 to the square root of n, so this will be like 2 point something. So now we have 5 2's, so we can write that down. So we have 2, 2, 2, 2, 2. Now we just loop from 3, to the square root of 5, which will be 3. It'll be like 2 point something. So now we just have to check, is 3 a factor of 5? No, it's not. So we're done with this loop. Finally, we check part 3. If n is greater than 1, add it to the factor. So we had 5. So the factors of 160 is this, and you can see how in practice it's significantly faster than just going from 1 to n, right? Like, it's especially for a big number. Like let's say our number is like a billion. We just divided by, like, we could divide a billion by 2 a ton, and then we would have a way smaller number, and we take the square root of it. So in practice, it's going to speed it up drastically. So that's kind of the way to do it. Now let's take a look at the code. So I actually have it up here. And this is going to be pretty much exactly what I said. So if we take a look, we have our result array, which is the factors. While we are able to divide it by 2, let's just keep dividing by 2 and add a 2. And then we loop from 3 to the square root of the number, and we go by every 2 numbers. We only check odd numbers. If the number is greater than I, we will never have a factor that's good anymore. If I is a factor, we just append it and we keep dividing. And we keep doing that over and over and over. And then finally, at the very end, if our leftover thing is greater than 1, then we also append that. And so you will use this in like a bunch of problems. I think I've seen it in like 4 or 5 problems so far. And so it is kind of useful to know how to do this in an efficient way before doing the problem. And let's just talk about one a little bit advanced use case of this, and then we can be done. So going back, let's say we have a number a, and a is a multiple of b. So a equals b times k, right? Where a is a multiple of b. So now, basically, we need to know if a is a multiple of b, what if a squared, and this was in one of the hard problems recently, is a multiple of b, right? So let's say for this example, let's go back to this 160 example. So let's say b is 160, and a squared is a multiple of b. So how do we know what numbers a has to have? Like what numbers does a have to have for sure, at least, to be a multiple of b? So notice, for one thing, for a to be a multiple of b, let's just do this part first. For a to be a multiple of b, that means that a has to have at least b. So if b has these prime factors, that means a has to have all of these numbers. So a has to have 2 times 2 times 2 times 2 times 2 times 5 times some other number, right? because this is 160. So A will have all of these numbers times this K here for A to be a multiple of B. So now the question is, what if A squared was a multiple of B? What would A have to have? Well, if you think about it, if B has a bunch of, we'll talk about this example, and then we'll talk about like the generic case. So if B is made up of these factors, if B has 5 2s and a 5, that means that A squared has to have at least this, right? At least all of these numbers in order for B to divide into A. It has to have it. Like it has to be at least 160 and then some multiple of 160. That means that if you think about what A squared means is if A has some prime factorization, like so let's just do a basic example. Let's say A is like 6, right? So A will have these factors. So what is this squared? This squared, every single one of these factors will just show up one more time, right? So it'll be like this. 6 squared equals 36. So we have a 6 and we have a 6, right? So when a number has a prime factorization, that number squared will have double for all of those numbers. So now going back to this, if this is B, what does A have to have? A has to have half of these, right? And then when we square it, all of the numbers will double, and then we'll have this. So we can write this down here. So we have 5 2s and 1 5 in B. So if A squared has to have at least this, that means how much does A have to have? So 5 2s, right? How much does A have to have here? Well, A can't have 2 2s, right? Because if we have 2, then A squared will have 4 2s, and that's not enough. So A has to have, for each number in B, we can write this down, for each prime factor in B, A has to have that factor divided by 2 rounded up, right? Because if there are 5, then A would have to have 3 to get enough, right? Because then if we have 3 and we double it, then we'd get 6, which is more than 5. We have to have more or equal. But if we only had 2, if we rounded down 5 by 2, then A would have 2, and then A squared would only have 4, and that wouldn't be enough. So A, if we have 5 2s, A would have to have 3 2s. And if there's 1 5, if A squared has to have 1 5, then A obviously has to have 1 5. It can't have 0. So A would have to have these numbers. And if A has these numbers, then A squared would be would work. So what is this number? We can calculate it really quick. So this is 40, I think. Right? Yeah, 40. Then A squared would be able to divide by 160. Obviously, this can. This would be 1600. But this is the smallest number that would work. Like nothing. So even though we're kind of overshooting by a bit, there's nothing smaller that squared would divide into 160. So hopefully that makes sense. Because you can't just like have the square root of 160, let's say, because the square root of 160 would be, I'm talking about like if you have actual integers, right? If A is an integer and B is an integer, because the square root of 160 would be, you can tell from the prime factorization, wouldn't be a whole number, because if the prime factorization has odd numbers of factors, then like it would be basically the square root of 5 times the square root of this whole thing, and neither of these is a whole number. So the square root of 160 wouldn't be a whole number, and we can verify that. So we just do like S squared T 160. Yeah, so we don't get a whole number. And so, yeah, so that's kind of like, hopefully that makes sense. For a number to be a multiple of another number, it has to have at least all those prime factors. So if we want the square root of that, we'd have to make sure that that number has at least half rounded up. So that's kind of like an advanced or a little bit advanced utilization of prime factorization. Most problems will ask for something simpler, but definitely important to know like what it is and an efficient algorithm to do it, something like this, which is much better than just like the brute force. So hopefully this was helpful. This is a little bit shorter one, not super advanced, but I do see it a lot, and people don't really talk about it, and it is not that easy to do if you've never seen it before, so just wanted to describe it. And let me know if it was helpful, and if it was, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.